So in this video, we're going to do a very quick refresher on what is the BraKet notation for vectors, something which we've been using in all our quantum uncertainty videos. The BraKet notation was introduced by the physicist Paul Dirac as a particularly useful notation to talk about vector spaces defined over complex numbers. So where does this term BraKet really come from? Well, essentially it's coming from brackets. And if you think about brackets of the form denoted in the slide, where you have a left angular bracket and a right angular bracket coming together to form a bracket, the right angular part is known as the ket, and it's typically used to denote in a shorthand form a column vector. Likewise, the left pointing bracket is called a bra, and it's used to denote a row vector. Now, if I'm going to create this row vector from a column vector, there's one additional step in constructing the entries of this row vector. So let's say you have a column vector which we represent as a ket, and I want to write its corresponding row vector. So obviously you're going to convert the column into a row, but at the same time what we do is we complex conjugate each of the entries. So essentially the entries in the bra vector are complex conjugates of entries in the corresponding column vector or the ket vector. When these two vectors come together, that denotes taking a dot product between the row vector and the column vector. So let's take some examples in the next slide. So as a very simple example, let's first take a real vector space, which means you have vectors defined over real numbers. Let's say my ket is a two-dimensional vector or a two-dimensional column vector with entries 1 and 2. So the first entry is 1, the second entry is 2, and we have written it as a column vector. If this is the ket, which we can call ket A, then the corresponding bra associated with this ket would simply be a row vector with the first entry 1 and the second entry 2. That's all there is to a ket and a bra. This time, let's again take a two-dimensional vector, but let's introduce complex numbers into our vector space. So for instance, I might have a ket B with entries 1 and I, just like you can see on the slide. So you see that one of the entries is real 1, but the second entry I denotes the fundamental complex constant I, which is the square root of -1. Now the bra associated with this ket would not just be a row vector, which is 1i, but it will be the row vector with entries complex conjugated. Now we know that the complex conjugate of the unit complex number I is -i. So the corresponding bra vector would have entries 1 and -i. Now let's continue working with the examples we have introduced so far, and this time let's bring the bra and the ket together to construct their inner product, or the generalization of what is the dot product. So for instance, if ket A, which was a column vector with entries 1 and 2, combines with the corresponding bra A, that just denotes the multiplication of the row vector with entries 1, 2 with the corresponding column vector with entries 1, 2. And the result we obtain is a real number in this case with the value 5. Now we can do the same operation with our complex vectors. So for instance, we have ket B coming together with the corresponding bra B. This time when I take the dot product, the net result is the real number 2. Now I can also construct an inner product between two vectors, or rather a bra and a ket, which are not coming from the same vector. So for instance, I can take the inner product between ket B and bra A. Now this time when I take this dot product, I'm multiplying the row 1, 2 with the column 1i, and the net result is a complex number 1 plus 2i. Now notice one very interesting thing, that when ket B comes together with bra A, this operation is not the same if I interchange the order of this coming together of A and B. So for instance, ket B combining with bra A is not the same as ket A combining with bra B. So in the last line, you can see that when ket A combines with bra B, the result is 1 minus 2i, which is the conjugate of the result we obtained when ket B came together with bra A. In general, bracketing AB, for instance, ket B getting bracketed or coming together with bra A, gives you a result which is the complex conjugate of ket A coming together with bra B. And this is a very important point to remember. Well, there's another very useful operation to be familiar with. We have talked about the inner product, which is when, let's say, ket A comes together with bra B and you construct the inner product. We can also define what is called a outer product, or what is sometimes in matrix notation is called a matrix product. And in this case, what happens is I have a ket A, which is a column with multiplying bra B. For instance, in this example, I have a column 1, 2, which is multiplying the row vector 1 minus I, and the net result is a matrix. Now you can do this operation with all the examples of the kets and bras that we have talked about so far. So for instance, when bra B, or rather when ket B comes together with bra A in the order that we have written on the second line in the slide, you get another matrix. Likewise, ket A can come together with bra A also to give you another matrix, and likewise ket B can come together with bra B to give you yet another matrix. Now, what is the physical meaning of all of these operations? We'll see in future videos. This was just a quick refresher of the mathematical notation, BraKet notation, and how you actually use them when you represent a ket as a column vector and a bra as a row vector.